Thank you very much for coming here this morning. I'm going to talk to you about oleogels. Remember, we talked about fat crystals. The problem was, can we make, if I convince you that maybe fats are colloidal gels, can we make a colloidal gel without actual crystals? Or with a weird version of the crystal? We can make butterflies out of, so everything you know about hydrogels, you can translate to oleogels or organogels if you work in that area. But there's quite a few edible, well, almost edible ones, that you can make stuff like this and pretend that this is a piece of butter, if you want to call it like that. And that's the challenge, but it's very qualitative. Not that much is known. Maybe you should get into it and try to clean it up, because every system is different, right? Every system is different. So, but before I do that, because I have, forgive me, Gareth and Suzanne here, I just wanted to make a couple points. I was like off by nothing yesterday to finish. I just want to make 5 minutes worth to finish yesterday's lecture so you understand where I'm coming from. I don't have time to get into it, but so eventually after talking to you about USACs and the fractals and the flocks and then particles make flocks, flocks pack, they pack into a network, you know, etc., 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 the usual thing. So we adapted it to fats. So eventually we came to the conclusion, we never knew what the particle was at the beginning, but you know, maybe it is that nanoplatelet that I talked to you about, and you have something that is a blob, a flock, meaning I have no real idea what this is, but it's some sort of correlation, length, coherence length of the system that is bigger than the individual particles, and you have about, I don't know, a few thousand particles in there. Nanoplatelets make sense. And so the idea here is that where we differ from other people is that in this model, this has to be completely close packed, otherwise your volume fractions don't work. You can get into that afterwards. And the other one is that we are talking about the links between chains. And it's a one-dimensional treatment in which basically you squish this thing, as I'll show you before. So that was the proposal. And I showed you this, but anyways. So, and we propose at the moment, and I'll show you why, that, and Gareth was asking this question, like, why are you saying that they're like fractal, right? So we proposed that they're stochastic mass fractals, and we got yelled at because like these things only existed within limited ranges of length scales. So people, how many decades? I'm like, one, haha, you know, and that kind of thing. You know, I had to weather a lot of abuse, and but we observed basic things like a scaling behavior of the elastic constant with a volume fraction of solids, sort of straight line, and I call it D, but with a power law that we assume it's in the weak link regime, and we end up with numbers that are more or less related to what people that simulate colloidal aggregation were getting. Even though I had so many discussions about what lives in 3-dimensional space and 2-dimensional space, you wouldn't believe it. Still, people frown at you if you put fractal dimensions of 2.5 and still yell at you when you do that, but I don't know why still. And then we also had a microscopy technique. We would analyze an image, and we would take a center of mass and see how many particles go from the center of that object outwards, and see how that density sort of correlation function would work. And we were getting slopes that were consistent with what you would think of a power law scaling behavior. So we had two lines of evidence. We had the microscopy evidence, we have this evidence, but we were still figuring things out. We did a whole bunch of experiments, which I don't know, really, we were looking at how the size of the cluster scales with the volume fraction and the power law, and we were getting, these are the kind of systems. This is very bizarre because these are spherulites. So we were like considering that these are actually clusters of crystals under these, and even under these circumstances, we actually get scaling behavior characteristic of a fractal object. And we were getting, again, fractal dimensions that people don't scream at you when you put 1.7. And other kinds of behaviors that suggested fractality. So it's interesting because it was mentioned before that we can have fractal rheological behavior. Not necessarily, that was Emanuela, remember? She said fractal rheological behavior even though the system that she has is not fractal. So it's like, ooh, that gets really funky. And another thing that really bothered me at the time is that always people like to talk about fractals at the critical concentration when the structure's just forming, right? When you don't have these densification artifacts that could come up. But we could see the scaling behavior go all the way into like a more concentrated system. And Buscal in 1988, the famous Buscal, actually said, I have no idea why this behavior survives in certain colloidal systems. So, The way I see it is you have a Christmas tree and you decorate it. Have you seen those Christmas trees that are covered in decorations? At the end, you do not know there's a freaking like Christmas tree behind it, but if you shake it, it's still there. The basic structure is there. So every time I see high volume fraction fractals, I think of the Christmas tree. And so the treatment is very basic, like arithmetic. You just basically compress or pull a system of close packed clusters that have a certain distance. You have a cluster size, you have a particle size, and you have a very basic one-dimensional deformation. And all you're doing by this is like an elastic constant is just the number of flocks and a link force constant between them, and which is related to the size of the cluster, right? How many you have in one dimension. And that's how Xi et al. Did it in 1990 as well. And they came up with the weak link regime and the strong link regime. In their view, this can also be squishy. In my view, this is hard and this is squishy. Weak link, strong link. Which one is squishy? And so again, Gareth, we saw it because we saw this fractal rheological scaling behavior. And that's where it all started, work of Brown et al. From Cambridge, simulations, and he's guilty for us going down this path. And so you could do a lot of things, like the solid fat content. That would be our volume fraction of solids. And so you just do a log-log plot, and you get really, really nice behavior for different systems. Some of them are more power large, some of them are linear, if your fractal dimension is 2. And these, we're talking about cocoa butter, milk fat, palm oil. This is not like pure molecules. These are like the stuff you eat in a sandwich, But the problem is, how do you characterize this? And we had to create dilutions with oil and work at low temperatures so you don't have solution effects, dissolution. So this is what we would do as an experiment, is just dilute it with oil. And then measure the G prime. Dilute it with oil, let it crystallize, low temperatures, and then you create this range of volume fractions. You can criticize that too. I mean, I'm a little, and you get nice behavior from many, many different systems in which you just normalize your G prime by the pre-exponential factor of the power law, and you get this nice behavior that is related to the apparent fractal dimension of the system. And look at the range that we get in natural systems. Yes, we get stuff around 2, which people can talk about DLAs and RLAs or cluster aggregation, but we also see these very densified things. Forgive me if I say something wrong, but I mean a DLA in 3 dimensions is around 2.5. So, but we also said, well, this dilution thing, can we do it also by just measuring the content of solid as a function of temperature? So you're changing it by just melting it a little bit. And can we measure the G prime as a function of temperature? And then we use one with the other one, and you can create this is anhydrous. So then obviously you end up with a G prime as a function of SFC because you measured both SFC and G prime, just plot one against the other one. And we found that both the dilution method and the heating method. So the other one is complicated, the dilution. You have to create dilutions, right? Make a whole bunch of samples, measure the samples, very controlled geometries. We have all these nicely controlled, if you need them, 3.2 millimeters by 2 millimeter size pieces in which we crystallize the fat so we'd have no funny shapes effects. And basically the slope that we get both from the thermomechanical method and the dilution method were the same. So you get a lot of fractal dimensions and a lot of pre-exponential factors. Now the model that I showed you yesterday, I just wanted to make a point that we derived that from thermodynamic arguments. We basically said, what is the change in energy of the whole system per cluster-cluster bond? We didn't do a mechanical, spring dashpot thingy, which we said, what's the total energy of that thing? Just divide one by the other one, total. And then what we did is we shoved in there like an expression for your favorite interaction force for a certain geometry, van der Waals, spheres, blocks, things, and you end up with something that looks like this. So I just wanted to point to the fact that you can go down that way as well. You don't need necessarily to look at a strictly mechanical model. You can actually go from energies. And then it's really nice because then you can use interaction energies. In this case, Hamaker coefficient. You can see that this probably came from just an expression of van der Waals interactions between spheres. So just in general concept, that's where that came from. And then this, because Suzanne is here, I wanted to say something. I mean, we ended up with, I don't like things that are too complicated. So we ended up with this strain. So we said, that's a strain in order for the math to work out, I needed something to fall out of it. So it's that you pull the clusters until you basically have no more interaction energy. And that would be your critical strain. And I thought that that is a yield stress, when you just don't feel each other anymore. And then you start flowing. Maybe it's not correct, but that's the assumption of this model. But the nice thing is that, if you do up deformation times a modulus, you end up with a stress, right? And that is the yield stress, and then everything goes away, and you end up with a really simple expression. And then you can at least, but this would be highly idealized system, right? Highly idealized, little spheres and flocks, and everything is close packed, and the world is beautiful. And things that you can measure, like particle size, interaction forces via the interfacial tension. You can shove numbers in there and see what numbers you get, and they're not bad at all. But of course, the problem with this treatment here is that it's very hard to predict the fractal dimension. So this becomes a fitting parameter. And I mean, if I tell you it's 2.5, 2.3, and it's Monday, it's 2.2, and it's Thursday, and it's 2.4, and it has a huge effect. So people get less excited about that. But in fact, people for many, many decades have said that this yield stress is a function of many of the amount of solids that are in there, the structure that is there. So it's a real indicator of functionality, like Hayton did in 1959 with the thumb tests, as I showed you. So it's very important to put a number to that yield stress because it does relate to a lot of the functionality. Now, defining it properly, as you know, is extremely difficult. I show you the simulations and the fact that it fit the data really, really well. And we extended it to the case where you actually have heterogeneous mass distribution. Those clusters are not close packed. So there's holes and stuff like that. And it gets more complicated. So yeah, we did publish it. It's a modification, but it's more complicated. I get a headache. And when the equations get too complicated, but you're welcome to go and see it there. And this one here, in case you know, we also developed a model for the particle field networks, composites. The elastic modulus is a function of volume fraction, the honored tradition of, that starts with the Einstein equation, the little expansion in the polynomials. But we actually called it a power law. And we build it from there because it fit the data a lot better. But it also addresses this heterogeneous stress distribution in this way. When you actually have linear transduction of stress, or you have heterogeneous transduction of stress, or if you put like a filler in the middle of all of this, and that distributes the stress in different ways. And that's part of what we developed over there. Now, just very quickly, as an example, I wanted to show you what the perfect roll-in fat. This is the fat that you use for croissants. So now this is like the test and stuff. And how do you create the structure that is here? And what are the properties that you require for the perfect croissant fat? And it's very popular. You have many books written about it, even like the croissant murder. So it's extremely interesting. You try to Google how many things on croissant are in the internet. It's really, and a lot of nice products that we eat are based on this. If you actually took a picture of the dough, what you're requiring your fat to do is dramatic. This is the millefeuille, that kind of thing. So you need a layer of dough, a layer of fat, a layer of dough, a layer of fat, and these are microns thick. So the sheet, you extrude a piece of dough that is yay thick, and yay thick, and you put in the middle of it a piece of fat that is yay thick. It all extrudes through a hopper, and then you fold it on, and then it goes through a roller, and the roller just like you would do in the kitchen, but these are industrial ones, and you start folding it and folding, and you have to preserve the structure. You have to separate layer to layer. If you don't do that, when you bake it, the water that is in the dough, there's a steam expansion. It expands and makes like an accordion. If all the little layers of dough are like sticking to each other, you have those bad crescents that you buy in North America that are not real croissants. They're like crescents. They're more like bread. They're not like expanded croissants. So very important to keep that. So if you have a lot of breakage of these layers, a bad croissant. So, and it's all related to the fat. The fat has to be very plastic, but it has to be firm. And you cannot have like chunks breaking off. It cannot be brittle whatsoever. It cannot be too soft either. So we started a project in which we got a lot of shortenings from industry, and they were like the all-purpose shortening is what you would use to make a cake, like Paul was telling us yesterday. And the laminating shortening, very expensive. you need in order to make this nice laminated product. So you take a picture, the rheometer with the glass window underneath, and you have the roll-in, because it's rolled-in shortening, and you can squish it as much as you want, and there's no cracks. You take the all-purpose shortening at the particular temperature. Obviously, temperature control is critical, right? That's why if you bake with butter, you really have to know what you're doing with croissants, because there's only a narrow range of temperatures that makes a good croissant. If it's too cold, you break it. And if it's too soft, it leaks out. So it's very difficult to make good, I think, very good croissants with butter. Butter's temperamental, and that SFC temperature profile is very sharp. But if you put the all-purpose, look, it cracks. And if you just squish this thing, what was it, 10%, you get laminating fat just and look, it looks pretty good. If you do the roll, this is the rolling fat, the laminating. If you do the all-purpose, look, you already have cracks. Brittle plastic, brittle plastic. And look at that, you guys like dye swells, right? So if you squish in a syringe through a little opening, these two things came out of the same opening, believe it or not. This is the laminating fat. You can make the spaghetti, probably you've done it. And otherwise, if you have the all-purpose fat, look what it does. Look at the dye swell that comes out of it. So it stores a lot of energy, then comes out of the other side and and here. So very interesting that two fats that you buy to make your like croissants or cakes can be so different. And exactly the same size. That is a huge amount of dye swell. And there's lawsuits to prove it that I'm involved with, because they ruined the life of a poor Indian lady with her son during the pandemic. They had this big contract with the supermarket, and they were making little pies. And they bought the wrong fat to make their laminated pies. They lost the contract. No more business. And so they came screaming at me to go to court with a bad, evil multinational company that sells them crappy stuff during the pandemic. And it's actually quite dramatic when you see it. You open the fat, you see chunks. So they have recrystallized, they form large aggregates. You do like that and it breaks off. You would think that you wouldn't go, that you would do a thumb test, right? Why buy all this fat, make all this product, give it to the supermarket and it's crap? I mean, when you get it, you should stick the hand. Do that with your experiments, unless it's like acid or something. Stick the hand in the experiment and go squishy, squishy. You got to feel it, right? And I would like here, thank you, Gareth. And thank you, Randy Ewald. We did nonlinear rheology. And you know what? I mean, you probably are all experts and stuff. But us food scientists, I found there's MIT Laos. Fantastic. I can just go here, and I urge all the experts among you to do more crap like this. Put out there a resource that most of us can use so we can have proper data out there. So we downloaded MIT. We did this work also in collaboration with Randy Ewald. We met him. We published together on this. You can download MIT Laos. You can just, it's like, I don't say plug and play, but it's almost plug and play. And then you get good results. So thank you very much for this. And we did the nonlinear rheology, and then Paul uses our data, and he used himself the data. You see, it propagates all over the place to the point where even physics today, like a quick study on the croissants, and that's Braulio. Macias Rodriguez, a prof at Urbana-Champaign, Illinois. He ended up right next to Randy, and he's trying to make his statement here. And look at this. This is the stress-strain curves. This is the all-purpose shortening. Look at that stress accumulation, and look at that yielding, and look at the nice laminating shortening. It's almost like you don't need to do like Laos, after you got that. It's like, what the hell? It's like. And we did the shebang thing. Here's the stress-strain. But it worked extremely well. I'm not going to talk to you too much about it, but let me just show you the basic result. Gareth talked to you about the moduli that you can get either at zero strain in the middle or at the very tip of the oscillation. You can get all these nice moduli or the Chebyshev polynomials and then correlate it to things. So in the end, this was the difference between the laminating shortening is the blue. The gray, and the all-purpose shortening is the blue. These are the elastic responses. And if you do it as a function of strain, if you just step back, it doesn't matter that it's local, or average, but they more or less look the same. So there were no differences in the laminating shortenings in the nonlinear moduli for the elastic component. No differences in energy storage. Thank you, Gareth. But there were huge differences in the viscous component. And it makes sense, right? You're going, and the thing is dissipating the energy like viscous way. It's not breaking, it's maintaining that viscosity that you want. And so that was interesting to see that that always the laminating shortening had a higher viscous component for all of them. So it was a very good, and then you saw Paul, when he saw yesterday how he was discriminating between good and bad shortenings. He could actually do it and say these work, these don't work at a plant level. So this thing works as an indicator of functionality for different fats that they were using. So that's cool. You wouldn't get this from G primes and G double primes. You wouldn't know what you're talking about. Higher viscous dissipation in the roll-in. Good enough for me. But here's the important point that I wanted to make. Why? Why are they different? What I learned also something here is like rheology without morphology is theology. I'll never forget that. So this is like what we need to do. We need to do, remember all those nice ultra small angle X-ray scattering? Here they are. Roll-in versus, and I want your opinion about this. After the analysis, remember how I showed you this part here was the surface of the nanoplatelet, then you have the aggregation into a mass fractal, then you have further aggregation into a mass or surface fractal depending on the day of the week, and you have the RG, which corresponded to the knees of these things or elbows of these things, right? So we have that. We use the unified fit model of Bocage, marriage of Guinea and Poro, and what do we get out of this? So what do we get? The roll-in shortening is here, and these are commercial ones, 20 kilogram boxes from the store, made by the big machines. And these ones here, they didn't know we were doing that with their samples. A lot of Cargèse samples do. But I mean, we just get samples from everybody and then analyze them and see where they are, but we didn't disclose where we got them from. But notice immediately that for the roll-in shortenings, you actually have 3 structural levels. There's 1, there's 2, and there's 3. And for the all-purpose shortening, which was brittle, we only have 2. So my proposal to you is that plasticity is related to the number of structural length scales present in your material. It's almost like when you have a cage of a car, you crash into a wall, that you almost have multiple yield stresses along the way, and each yield stress belongs to a certain length scale that is present in the material. So you break one, it's a cascade of failures as you go along. Maybe, maybe not. It would have to be also reversible, but these materials tend to be highly reversible as well. They reform the van der Waals interactions. So look in this case, for the roll-in shortening, we have fairly small nanoplatelets, effective sphere equivalents, 35 to, again, this is a little off, but I mean 50 nanometers in size. That's an effective size. We also have fairly smooth slopes for those, close to the Poirot slope of 4, that corresponds to a flat, perfect surface. Smooth, small, smooth and small, SS, smooth and small. And then we have also another length scale, which makes quite a bit of sense. So something extremely small, then something around whatever, 300, 400 nanometers. And then you have something in the larger range. And what about this one here? You have sort of a mass fractally kind of number here. While in this case, in the all-purpose shortening, you have a very large primary unit, or first structural level, with a rough surface. So I don't know, think about many bumps on top of that nanoplatelet surface, irregularities. And then you have a very large one. And this is more related to like a strange either surface or a diffuse pore-like structure, depending on if you reach Schmidt or not. So you go from there to there. So the way I see it is that you can have a gradual failure at different length scales, while in this case you accumulate all the stress and then you blow up. It's like an old Mustang versus a new Mustang. You better crash into the new Mustang. Otherwise, you go with this big piece of metal, you crash against the wall, it accumulates under the energy, and then there's an explosive or catastrophic failure of the whole material, as opposed to the new cars that have more structural length scales. So that was our smaller CMP units with smooth surfaces and 3 structural levels in the roll-in versus the other one. Yes, sir. Yeah, so this would be the RG, that point of inflection between side to side. This would be the characteristic slopes associated with the other one. And this was the range of that particular length scale. Because in the Bocage, in the unified fit model of Bocage, you have to tell it where the length scales are. Yes, sir. Oh, this, yeah, yeah. 6 divided, oh, thank God it's in angstroms. About like 6 divided by 0.1, 60 angstroms, 6 nanometers. And that corresponds to, you're looking at the 001 reflection. Not very well. It's a Bond's hard camera, so it's like crap for diffraction. Yeah. So anyway, so that's the. Oh yeah, and by the way, and when they make these fats, these guys, they roll and shortening, are extruded at the end, and they come in long boxes like this too. So they finish it up somehow with some sort of like, and look, they look laminated or shear banded as well. While the all-purpose looks more random. So there's, we didn't go there. That was too complicated. I don't understand why that is. They finish it off by extruding it. Okay, and this is the final test for the exam. Everything you've learned. So we have 2 fats now, 2 fats, and we have fully hydrogenated canola oil. It's 18 carbons long, all saturated in the triglyceride. And then you have high oleic sunflower oil. Think of it 18 with 1 double bond or 2 double bonds. So we're going to mix the 2 together at different proportions, and you can see the carbon numbers that are present in there. And then we're going to mix the 2 of them. This is sort of a chemistry thing, and see what happens. But this is mostly this is mostly stearic acid, 18-0, and this is mostly oleic acid. So you can think of this as triolean and tristeric mixed together. Now, when you do chemical interesterification, by the way, your parents ate interesterified fats forever without knowing that they were working on a modified fat. Becel margarine, the most famous margarine, is interesterified, and it was still interesterified, 20-ton reactors, sodium methoxide, fat, and what it does, it randomizes things. It takes all these acids and makes a random mixture of them. So you end up with intermediate molecular species. Look, you have OOO, oleic, 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 steric, 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 and you end up with the 2 original ones and all the possible isomers that would be possible from that. And now you have like a mixture. Mixtures are better than pure components in order to functionality, and that's just your equilibrium composition from a binomial expansion. It's like that. Very easy to do this randomization of structure. It takes like 30 minutes. You put the catalyst, you heat it up to like 80, 90 degrees, it turns orange, you add some water and acid, citric acid, and it's done. That's it. And you obtain very, very cheap to do. And look what happens to the melting profile. You have seen solid fat content temperature profiles. If you put a wax, like SSS, waxy stuff, in oil, it just hangs in there forever and ever and ever. It's just lower because there's just only, 30% of this high melting in the lower one. And then it eventually, your SSS melts at a very high temperature, completely non-functional, right? I mean, you put that in your mouth, it's like biting that romantic candle you were trying to convince your girlfriend to join you with. I mean, it just doesn't work. And then if you intersterify, you change that steepness of that melting profile. And look, that looks like something that would hopefully melt around your mouth and that kind of thing. So very nice, because you are creating the molecular species that would give you this higher SFC here and the lower SFC here in the randomization process. So that's a good thing. Now, if you look at the microstructure, it seems that you have more spherulites in the non-interesterified one, more of the spherulitic growth. You hit it with a catalyst, and you get maybe smaller of these clusters, if you may want it, and maybe smaller crystals. But one of the characteristics is that in the non-interesterified, now you know, 3.7, 3.9, 4.6, beta, triclinic. So triclinic, and then you dilute it with oil. It doesn't matter how much oil you do, it's the same pattern. You get the triclinic form. You remember how we learned that the triclinic form was grainy, high melting, not good for the food products? You saw that yesterday. So there's no change in the polymorphism of this upon dilution. Now, you hit it with the catalyst, and all of a sudden you get except for the 100% one, which obviously is not transformed. Look at that, 3.8, 4.2, and a little bit of the 4.6. If you read those tables, you'd say that's beta prime now. So by intersterifying, I made beta prime. This is how interesterification came to be in the 50s when they started intersterifying lard to make better pie crusts, make them more plastic, make it more smooth. You need a beta prime. Work with me here. I mean, this is how the food scientist in baking works. Imagine saying those big words. I need an orthorhombic perpendicular structure in order to make a very good margarine. It's like, wow, did you go to school? It's like that. So it's cool. I mean, they use this complex, extrapolate it to the ultimate extent. And now, the enzymatic, we also did it enzymatically. If you don't like chemicals, you're green, you're a hippie, you have you like enzymatic. I only do enzymatic. And then you also get the 3.8, 4.2 with a little bit of the 4.6. It's like, damn, beta shows up its face from time to time. However, we've improved on it. One curious thing is that this highly saturated one, if you cool it down even to room temperature, you get the alpha form. And it doesn't transform to the beta or beta prime for days. So, what happens when you intersterify? Let's take the example of chemically intersterified and non-intersterified. 80% solids. When you actually do a yield force, cone penetrometry, hardness of the material, you find that the chemical intersterified one is softer, has a lower yield stress. So we start there. So you go, oh, obviously it has less solids. There's less solids present. However, the chemically intersterified in the range where we measured at 30 degrees, the temperature has more solids. So it's softer and it has more solids? What the hell? So what we did is like, okay, let's find the culprit. So we put together everything we've learned in this lecture is like, let's do that Fischer-Turnbull analysis and get the crystal melt interfacial tension, just to see if there's some effects in there. And these are just different amounts of the fat in the oil to get the whole range, just for many, many different samples. So what's this one here that is higher? This one here is the non-intersterified. So we intersterify, we randomize molecularly, so now everybody's more the same as opposed to very different, right? Solid and liquid. And look at that, we lower the interfacial tension between the two. That makes sense, right? It's almost like emulsification. You made that interface so much less different between the solid and the liquid because the average molecular composition is more similar. And enzymatic and chemical, thank goodness, they're about the same. So we lowered that interfacial tension. And remember the term in the model, that's up there in the numerator, and that's your strength of intermolecular forces. So you would say it's made it weaker. Maybe. So here it is, right? We decrease that thing, and the yield stress goes down for the same amount of solids. This was obtained with the Desjardins approximation for spheres. And then we also determined the size of the crystalline nanoplatelets. Look at that, the non-intersterified, what is it, around 140 nanometers, and the intersterified, 100 nanometers. So we decreased the crystal size as well. Now, that is not very good news according to the model, because if we decrease the size of the crystal, it should get harder. So that's working against us. The interfacial tension, I thought, we got it. And then we checked the crystalline nanoplatelets, even though you can argue that putting one number to that distribution may be a little silly thing to do. But we take the median of that. So if you calculate the yield stress, this is a 30% reduction in the size of the nanoplatelet. And then if you divide the interfacial tension by the particle size, which would be this pre-exponential term in here, you lose about 45% of going from there to here, non-intersterified, you lose 45% of the value of that. And when you decrease the yield stress from 206 newtons to 114 newtons, you're losing about 45% of the yield stress. So we thought that, unfortunately, I just wanted to show you that you can have effects, but they're like the two things show their heads. Both the crystal size, which smaller should make harder, and this one here, which decreased, which should make softer. But both of them were fighting against each other, and it's this interplay between the size of your crystal and how strongly they interact. Makes sense? It makes sense, right? I mean, it would be nice if it was controlled by one. What I'm saying is that tomorrow I do this experiment in another system, and it'll probably be a different behavior. But at least you got a framework to understand what you're doing. Maybe you should be messing around with the interfacial tension by adding surfactants. And so you add a little surfactant, you can change things dramatically. Why? Because you're changing the interaction between the crystalline nanoplatelets. At least it allows you to think a little bit, even if not try to predict. You would hope that it's predicting. And so that was the test thing at the end. So can we repeat this? The dream here is to repeat this with an oleogel. And so this is a butterfly by Arenbot from Unilever. We published on the same year about organogels. I think they did it before, but you know, in industry they restrict your publications, so we came running, and we have the first papers on edible oleogels in 2006 that came out that were his oryzanol, we'll do that, the oryzanol phytosterols, really exciting system that you should be studying, and the hydroxysteric acid that we were, hydroxysteric acid type family organogel. So this is a butterfly he made with the oleogel. And so there's different strategies to get to structured oils. And the idea here is like, can we remove saturated fat? Can we remove hydrogenated fat and create a material that has the same elastoplastic properties, behavior, yield stress, plasticity, melting point, and don't forget the flavor and the cost associated with that. In food science, we don't have the privilege of stopping and saying, oh, we just do it. We have to think about how much is that going to cost? Is it reasonable? Is it scalable? Is anybody going to buy this? So those are the extra components that are in the equation, which makes it sometimes a little more difficult. So what else? How can we make a fatty material? Invent something. So we can have polymer organogels. We actually have polymers that dissolve in a vegetable oil, the same olive oil you put in your salad. Can we dissolve a polymer in that? And can we induce gelation in the same way you understand hydrogelation, oleogelation? And the answer is yes, you can. There are. And everything you know about hydrogels, just turn it upside down and you have the oleogels. It's exactly the same. There's no difference. Structure, and my point is that the structuring agents usually have to be in a very low range. So again, you're close to critical concentration, so that should make you very excited. And then you can really like understand the system better. Now, besides polymer organogels, you can have fat crystal networks of high melting fats. For some reason, if you have extremely high melting fats, you can actually obtain a network that is percolating, that is firm enough, that spans the system, and you make something that is like a gel, like a colloidal gel. Again, 2 to 5% structuring agent. You can take that a little bit beyond that. You can have polycrystalline fibrillar and particle organogels. I don't want to call this SAFINs, self-assembled fibrillar networks, because that's just one part of the concept that you have a particle or a fiber or a fibrous structure that makes a gel. And I'll show you a couple of cases of the structure that you can form. They're absolutely insane. I mean, there's nothing that you would ever think of. Maybe you do. I didn't. And then you can cheat a little bit. You can say, can I make a high internal phase emulsion? Mayonnaise. You know, that eventually, it's almost like push that mayonnaise a little bit to become harder. It is fairly plastic. It will contain water, so maybe that's cheating, but that's not necessarily too cheating. And then these are some of the strategies you get in order to make I would like to call it a fat mimetic. Not to just leave it in the world of organogels, which should be anhydrous, right? Come on, you can have your water, use water in order to do it. So here are some of the strategies we were talking about. The building blocks of an organogel. I guess we're gonna not get into super detail, but so what are some of the crystalline particles and fiber? Monoglycerides. Self-assemble. Maybe you've heard of glycerol monooleate. They have rich phase behavior, lyotropic liquid crystals. They do all kinds of funky things. And they structure oil at very low concentrations, 2%, very metastable. You make your gel, you think you invented something, you go celebrate, you come back, it's all separated. Because it undergoes a I wouldn't call it a polymorphic change, but it's more like a mesomorphic change. Fat crystals, special fat crystals, high melting. Plant waxes. A lot of people use the waxes, that come from rice bran, from sunflower, very high melting component. They're esters of long-chain fatty acids and long-chain alcohols, and they themselves can structure oil at like the critical concentrations of 0.5%. So very nice. The only problem it is that you eat that and it feels that you're licking your car on a Sunday morning after you wax it. That's the only problem with that. But you also have certain emulsifiers that do this as well. You want self-assembly in the oil. So it's almost like saying self-assembly in water, like a biological membrane, but you need self-assembly in oil. And there's a few of you who are working on these oleogels. It is mostly at the beginning a fishing expedition. You can predict all you want, but it's very difficult to say that molecule's going to gel, even unless you have this stacking of aromatic rings. That's more advanced. But most of the time you're fishing until you find the system and then you try to understand it. Ceramides, again, surfactant-like molecules that self-assemble in oil, not in water. Now, you actually can have these particles, and these are not these fibers that you see in the literature. These are like little things, little crystals of waxes and stuff. Now, you can have nanofibers as well, which is really exciting. These things can self-assemble, like really self-assemble, and form like hundreds of microns long fibers. And these are fibers. This is not like meat fibers in made analogs. These are the real thing. So hydroxysteric acid is the most famous one. I bet you money. Go to your advisor, ask him to buy a little bit of hydroxysteric acid, put it in the microwave, melt it, leave it on your desk. You'll like go, oh my God, I must study this for the rest of my life. I mean, it's absurd, the structures that you form. And this is the most famous one, is phytosterols and oryzanol, mixed, plant sterols that are good for your health and stuff like that. But if you mix two of these similar molecules, sterol-like, think of cholesterol, but for the plant. And if you mix some of these together, you form that beautiful butterfly I showed you. And Adam Bott from Unilever is the one who published the first paper on that. And they form fibers. And I'll show you a little bit of the science behind it. And in the polymers, you can have physical gels and chemical gels. I'll show you the example of ethyl cellulose, which is the one that we worked on quite a bit. So again, as you progress in your career, people allow you to do color figures. So now this is the soft matter review in 2020, the different strategies. So you can have direct oleogelation. That's when you throw a molecule in the oil and it forms a gel. So I talked to you about natural waxes, fatty alcohols, surfactant-like molecules, fatty acids, hydroxylated fatty acids. And look at these fibril structures you form. I'll show you more microscopy. It's really cool, actually. And then these are the polymeric oleogelators. Look at that AFM of an ethyl cellulose oleogel, and look at those holes. These are microns in size. So you actually make a closed cell foam naturally with a good wall. Just take the ethyl cellulose, as I'll show you, put it in the oil, press the microwave, not too high, above the glass transition temperature of 135. It all dissolves, completely clear. Then you cool it down and you have this transparent thing, a polymer gel. Yes, sir? There's no justice in the world, my dear sir, because Dow Chemical owns pretty much the ethyl cellulose market. Even though there's many other oleogelators that deserve being food grade grass and allowed, Dow made a petition, and guess what? It got allowed immediately. No novel food thing. They put a petition, it's like, yes, sir, Dow, allowed. It's pretty much the only oleogelator allowed legally in foods. Unbelievable, unbelievable. But anyways, yeah, go crazy. Up to 5% is the law. And then you have the strategies of the structured biphasic systems. You basically make your favorite emulsion, either with monoglycerides or with proteins, and you can either leave it wet or dry it. Imagine if you that's how everybody's making protein oleogels these days. When you hear that, you make an emulsion with the protein, you dry it. And that chunk is supposed to be your oleogel. That's a cool idea, to use proteins to form structures and then you dry it. That's natural, right? You don't have to put ethyl cellulose on the label. You can just put pea protein. But Rafael Mezenga was the first one to actually do that. He made a really nice whey protein emulsion. He cross-linked it with glutaraldehyde. He dried it long time ago. And people have been trying, like Elke Scholten's group and Wageningen did a lot of this, like make the emulsion, dry it down, and now you have an oleogel, which is a basically dried version of something like this, made by proteins, and a dried emulsion, an emulsion-filled gel that you dry. All of them are the same. Choose your favorite polymer. It doesn't matter. So what constitutes a good oleogelator? We need to be able to predict these things, but I don't think it's possible because each system is so different from each other. I call at least the crystalline ones, the good crystalline oleogelator is a frustrated crystal. And it undergoes what I think is dimensionally restricted growth. So it doesn't do three-dimensional growth. It does one or two-dimensional growth. They're fibers or plates, not spheres. That helps in the self-assembly. Maybe it's a surface area related thing. I mean, you get a lot more surface area in case you pack it all in a ball as opposed to one of these extended structures. So let me give you the example of hydroxysteric acid. It's a very simple molecule, beautiful molecule. It's just 18 carbons long, saturated, and look, it has an OH group here at position number 12. And that matters, by the way, unfortunately. That is at 12. If you do at other positions, it doesn't work as well. And the work we didn't work on this first. We did work on this guy first, which is the same thing. You know, you got to steal sometimes, you know, things. And the only difference is that there's a double bond here. So it's not saturated, it's unsaturated. Not that it makes any difference because you add this at 1% concentrations, but this thing is called rinsenoladic acid. And so we have a bit of a state diagram of these things. Look, you can make translucent gels at 1 to 1.5%. And look, it survives not too bad till about 30%. That sounds like melting in your mouth, right? You can just maybe make a margarine out of this. A relatively brittle gel. Not relatively, really brittle gel. Unfortunately. And then you can get some more opaque regions. Then they're just more aggregated. And then there's, of course, weak and no gels at the low concentration, high temperatures, as we would expect. Now, the packing of the hydroxysteric acid has been studied by Tergeral from a long time ago. I don't know if you know, but this is a highly twisted version of that hydroxysteric acid molecule. And these are the OH groups that were jutting out. And it needs to line up in a very specific way in order to be able to form the structure. It's not trivial. And as I'll show you in a second, when this is what here's the interaction between the OH groups, and this is the rest of the molecule, and this is the these are the crystallographic axes are defined here, and this is the basic structure underlying the fibers that I'm going to show you. This thing does this, and then forms fibers, and look at what forms. And this is an 100 micron scale bar, and look at that. Gigantic fibers in your system, and anybody can tell me why you see dark and bright regions? This is a polarized light micrograph, so you're under cross polars, 90 degrees. They're birefringent, so you see this kind of stuff. And you see that because it's going like this. It's a ribbon. So you're like in phase, out of phase, in phase, out of phase. And so as it turns, it forms these long ribbons, which are, and if, of course, you rotate the polarized microscope, you see this thing moving, right? So they're not only fibers, but they're ribbons. And there's also branching. We studied branching quite a bit, to talk about Cayley trees and things like that, and look at all the patterns of birefringence. Now, if we remove some of the oil with cold isobutanol and do some cryo-SEM, you can still see the fibers. These are significantly thicker, but a lot of oil is all like adsorbed onto these, hence the super high surface area and the ability that this thing forms a gel at 1% concentrations. Oh. Is it going? This is watching a pot of tea form. Look at that. A pot of tea boil. Just cooling it down in front of you after you microwave it and you went for a coffee and looking at this thing. Well, maybe you don't see this. I don't remember. Don't remember. But it's fast. Like this thing gels the moment it goes underneath its melting temperature, which is around 70 degrees. So we would say that this would be like 5 minutes. And look what you form in terms of a mess of fibers and birefringent things and turny things. As you can imagine, you look at that and say that's amazing, but that's brittle, right? That just screams at you brittle. I'm gonna just touch it, and I'm gonna break all these things. 1%. And if you need to know, the critical concentration for these were about 0.5%. Now, our other system, I'm not gonna, I mean, this is the other version of the molecule. It's a little less efficient than hydroxysteric acid. Again, the clear gel here, less heat resistant. The one that had the double bond from hydroxysteric acid, a little less good of a gelator, but one thing to think about here, you have to think about the polarity of the solvent. And this is not super quantitative state diagrams, but if you make your gel in canola oil, you get the red is the good part of the gel, right? Now, if you put it in I don't remember that what is. Sesame oil. If you put it in sesame oil, you have shrunk it. Now, sesame oil, have you seen, like, have you eaten it? Has a lot of brown stuff. It's polar components in it. If you actually measure the polarity, now you're going to dissolve the surfactant, the hydroxysteric acid, more. And so if you dissolve it, now you have less gelling agent. You have to mind the oil you put it in. You put it in a diglyceride oil, and diglyceride is the triglyceride minus one fatty acid, so it has now an OH, and it's much more polar. And look, nothing. It doesn't gel. So the solvent, I guess it makes sense, right? The solvent plays a role in a gelation phenomenon. So you have to think of the oil as the solvent. And, you know, probably if you put it in olive oil, it's not going to work very well either, because the olive oil has many of those minor nice green components that you like for health and taste, and those things are going to mess around with the solubility of your gelating agent. And now, there's again, they're sensitive to external fields. If you set it at, for example, 30 degrees Celsius, you have these fibrous structures like I showed you before, but if you actually set it at 5 degrees, it's much more like fine-grained. And so you can affect the branching of these things. You get more nucleation. It's sort of a surface nucleation, branching. As the material grows, at 5 degrees, you enhance that much more than at 30 degrees. You have much more continuous growth. And you can then affect the migration, the mass of oil migrated. So the oil binding, if you want, at 30 degrees from the structures that look open like this, it makes sense, right? You got big pores. They're going to move more than if you have small pores at 5 degrees. So mind the temperature that you're making this material. If you want those big fibers for the publications, they got to be like, you got to leave them at room temperature. But if you want something that is a little bit more functional, you better put it in the fridge or cool it fast. Functional here, less oil loss, because you don't want your gel to just start leaking the oil like that. Very good question. There's a certain amount of syneresis that happens in time. The ethyl cellulose oleogels that I make are stable for many years. But these things you see, eventually in time, the material like retrogrades, if you want, becomes more compact and the oil goes up. But all you have to do is put a little more, and then that stops the retrogradation. And if you go up to 2%, it's fairly stable. Now, I do not know, remember the Paulson MR for solid fat content determination? You can actually, that machine is a really practical way of determining spin-spin relaxation times, or spin lattice relaxation times, T2s. I was talking to some of you about the fact that you can use to determine the T2 of water, which changes like crazy in hydrogels, like from 2,800 milliseconds to like 100, depending on what surface you present to it. So it's a paper generating machine, because I mean the changes are so gigantic and sensitive to surfaces. I highly recommend this fantastic 20 megahertz NMR that is Pulsar. The same one to do SFC. If you pay the extra money, you can do T2s and T1s. And you don't have to bother the guy with the 800 megahertz NMR. Could I run my like sandwich fat in there? And then they don't like you. But if you have your own, you can do a lot more. You can use it as a tool in order to determine if, for example, there's a difference when you gel it or don't gel it. For example, here we have the oleogel, just focusing on this, at different temperatures. So at 30 degrees, we see something, and what you get is an exponential decay. and then you do an inverse Laplace transform and you get distributions of species. It's the same as saying that this decay is multi-exponential and you have, I don't know, 3 families, 4 families of these things. And so it's up to you to interpret what these bumps mean. But we also interpret the ones that have the higher T2s to be like a bulk oil, bound oil, bulk oil, a little more bound oil, really, really bound oil. That's how it's used. You have to then figure out what the hell those species are. But you can really see the changes that happen with either concentration or here in temperature is actually quite dramatic. It just shifts as you lower the temperature. It shifts towards the shorter decay times, the shorter T2s. Solids have faster decays of magnetization than liquid ones. So again, a tool to be able to say something about oil binding. Now, what happens? Oh yeah, is it moving? Yeah. So what happens if we shear it? Look at that, we're weaving. And now we make bundles of fibers. You remember the fibers before? Look what we're doing here, it's nuts, eh? And this is oscillatory shear in one of those Lincoln shear cells. And we made a root. Is it useful? I don't think so, but it is really, really pretty. And you can change the structure of these materials like crazy again by external fields. We all did all our experiments at 1%. Yeah, always, because yeah, that's there's a practical limitation because these things are not expensive and they're probably slightly toxic. So and the utility of these things, I think, it's in the fact that you use 1%. If I have to use 10, 15% structuring agent, I'm just going to use a fat. Yeah. And this crystallization is around 25 Celsius. Sorry, I didn't say that. So there you go. You've woven a fiber. But look at that. So you go at like static conditions, higher temperatures, and you make this like a beautiful like piece of art. And then if you do it, for example, a very fast cooling rate, I don't know if you see it very well with this light, you have this fairy light, this gigantic fairy light at 30 degrees per minute. It's insane. It looks like this. And there's famous papers by, the group of Savan and Liu, and they talk about the growth of organogelators in this ferrolytic structure starting at a center, and it's induced by these high cooling rates. So you can do this just with 30 degrees per minute versus that, there you go, Gareth. It's 2.5% HSA in canola oil, 1 degree per minute. So 1 degree, 30 degrees. I don't think they align in the shear. I think that all you're doing, well, here, this is cooling rate. In the shear flow that I showed you before, it was oscillatory. So I was taking a picture from above, and this thing was rotating like this. So they would be orthogonal to that, yeah. Maybe they're aligning. I don't think so because it's oscillatory. It wasn't that much strain. But we did some of these things here. For example, we measured the yield stress of the oleogel. And I have a lot more data, but I decided not to show you. Anything you do to it, like shearing in order to fix it and to help it, decreases the yield stress. So you go from that brittle material to something that is a lot weaker. Look at that as a function of cooling rate. And also the G prime of these things can be relatively high for such low concentrations. Forget the fact that we have phase angle here, but look at the G prime. And if you increase the cooling rate, even though you make those big structures, you actually decrease the G prime of that one order of magnitude. Not order of magnitude, but one logarithmic unit there. So you can shear it, but in terms of small deformation mechanical stress, you make them weaker, and of course even the large deformation, you make them quite a bit weaker relative to the case where you have no shear whatsoever. So you wonder, it's interesting, you can change it, but you don't necessarily want this for a commercial product. You don't want to end up with a fat with a yield stress of 25. In the melting, probably not. It's all structure. It's all mesoscale. Again, the length scale that is controlling our rheology and controlling our oil binding and the macroscopic functionality is more like a mesoscale thing. At the other level, they all do the same. Waxes do that too as well. So again, oscillatory shear strain and microstructure. So we have the static one, and then you saw before where we make these bundles of fibers which can be 20, 30 microns in size. And what about this? The cooling rates and high cooling rates and increasing oscillatory shear. So we're at 30 degrees per minute, and we have this under very low shear rates or no shear rates, we get these monsters. I mean, this is 100 microns. So this is like, you can see this with the eye. This is how big these things are. You start like shearing it, and you make little versions of this, more nucleation, right? And they're all mixed into the other. So you can make a whole bunch of these spherolytic structures, if you want to call them that. Now, another system which is of interest to the biologists among you is the ceramides, which are natural components of biological membranes, either a synthetic one, and I'll show you what C2 means, or egg. Egg has a lot of ceramides, and these are used in cosmetics as well. And that's one of the things that these things are useful for. Aaron Bott and the Unilever guys were interested in this because you put it in margarine, you decrease the saturated fat, and you enhance the structure with the oleogelator. So now you can use less saturated fat, it's more healthy, and et cetera, et cetera. Now, the same would go for a cosmetic cream based on ceramides. It's used extensively. Imagine if you can make an oleo jelly thing, it would be a lot nicer on the skin. And ceramides look like there's here's the sphingosine. It's like think of a phospholipid, right? But this is sphingosine base. So you have a long chain fatty acid-like molecule. You have an amino group. You have CH2OH. And now this is sphingosine phosphate. And the ceramide, if you notice, they just have another they have a fatty acid right here attached to the nitrogen. This is similar to some of the structures of who was working on amidated. There was, I forgot, I saw the poster right here working on oleogelation. I don't think she's here. Oh, there you are. You were working, that's similar in principle to the ceramides, in which you create a derivative of it's an amide group here, and she's got oleogelators. This is naturally present. The ceramide has this type of structure. And you know, sphingomyelin, brain stuff, is in your brain. And then it has this choline group attached to it. So very interesting biological molecules have the ability to form gels in oil, surfactant-like. So this is the C2 ceramide, in which we only have like an acetic acid instead of the long fatty acid over there. That's how it looks, and we actually can form weird oleogels, but you can make a tree out of it. A little on the brittle side, I would like to say, but interesting. And then we also, so you saw those fibers with the pure components. So when you have a homogeneous system, a one molecule, you form these fibers, right? But then you have egg, and there's ceramide in egg, and look at all the fatty acids that are present there. That's the length of the fatty acid. Don't even go there, like 23, 0, 24. It's just a mishmash of different fatty acids. And what does that do? What that does is create particles. So this was an interesting transition that happened. Everybody who worked on oleogels think that you had to form fibers, and they call them saphins. I don't even use that name anymore. Because what I would like to have is not those fibers. I would like to have particles that allow me to stress it. They can slide past each other. They can reform in a way like a fancy fat crystal, right? That's what you want. Something that is highly effective at gelling the material, a colloidal gel, if you want to call it that, but that allows some plasticity in the system. And again, by increasing the complexity, you decrease the complexity. By increasing the complexity in composition, sometimes you have much more predictable behavior. And so this is, that's with the ceramides. They're too expensive. Maybe some fancy cream for somebody with some disorder, you can put a pharmaceutical in it. But, and this happened to this thing here. Aaron discovered that you can take beta-cytosterol, which are present naturally in oils. They're very healthy components. They help your cardiovascular health. They help you reduce cholesterol. There's clinically, if you eat like a lot of cytosterol, it competes with cholesterol in your gut. And so it binds where cholesterol would bind, and you excrete the cholesterol. And you have to eat like 2.5 grams of this thing for like clinical efficacy. So that's crazy, but there's a lot we should be doing with these phytosterols, which are the byproducts of the refining process of oils. So they're waste products, believe it or not. They take it out of the oils, they sell you like funky oil, and they put it in pills, and they make double the money. Same with the vitamin E and all those kind of things. They distill them off, if you want to call it. If you mix beta-cytosterol with this ferulic acid, right? And here comes the magic of this. At a certain ratio, you make gels. And a certain ratio. This looks, I don't know if you see it very well, but this looks, it's much more coarse. These are your clear, transparent gels at concentrations of, this is 100, 80-20, 60, 80-20, 60-40 to 40-60, in that range of half-half. Half-half oryzanol, half-half cytosterol, you make these really clear gels. And look what you make. Now that is nice. Imagine the papers. There's no end to this. You give that to an editor in color, you get the cover. I mean, it doesn't matter what you say, but it's interesting. And if you promise that you can control somehow this, then that's really interesting. So for your own benefit to see sterol and oryzanol combo, here you have the cytosterol attached to a linoleic acid, because they're like attached to fatty acids, 2 double bonds. That's where the name linoleic comes from. But here's the cytosterol, or it's a phytosterol. Cytosterol is a phytosterol. Phyto means from plants, and cyto is this guy. And this is the oryzanol as well. They need to be together. But there's other bases that form, believe it or not. You can do it with cholesterol as well. Cholesterol has some rich behavior in terms of self-assembly. And it all happens right here in your gut. But look at all the possible phytosterols and sterols and that you can work with. Now, Aaron also did some really nice sacs, and these are some of the data that he had. You actually can get very clean things, and he fitted to a hollow cylinder model of Deutsch. Here it is with certain simplifications. You can read it in his paper and stuff. Of course, it's not that difficult. It's just this is the structure that he came up with. A hollow cylinder of about 72 angstroms in diameter. And he had to consider the radii, the internal radii, the outside radii, the size of the wall. All of those things belong in the model that you have in there. Very interesting structure, really nanoscale at 7.2 nanometer. These things are really nanoscale structures. And some people were excited because maybe you can put things inside. Complications, as always, if you set the material, like it's not as easy as just putting it on your bench. Look at the differences in G prime that you can get from, this is 6% sterile, just to make, to qualify for Gareth. It's not as strong as you would think. You're working at, well, you're 10 to the 5, right? 100 kilopascals. 100 kilopascals is not that bad for a 6% structuring agent in oil. But you actually affect the nucleation and crystallization of behavior, the self-assembly of this is, I would say, a slight function of that. So beware that the temperature plays a role like we said it. So just don't blindly go where no man has gone before, like catalog a little bit what you're doing. Don't make the experiment in winter and summer and then compare it, you know, put it in some sort of ice box or something. And also the yield stress under compression or shear, you get an idea that you can get 100 to almost 300. That's pretty decent. Yeah. Sounds pretty huge. That's his work. One would have to double check if he made a mistake on that label. I would call it more like pascals, right, than kilopascals. Depends on what he defined as it. And notice that we said that about half and half, oryzanol phytosterol, just keep that, half and half. Unless somebody asks you to decrease the price on this, you may have to go lower. But the maximum structuring occurs, like we saw before, at some intermediate range of equal sharing of phytosterol and oryzanol. It's a 2 molecule self-assembling with themselves. So what are we going to use these things for? A lot of things. This is the food science coming out. And one of them is not going to be going to the next slide. There. So what about encapsulating bioactive ingredients in there? Why are you doing this? So beta carotene is the orange component in carrots, right? And what we did is we put it in a hydroxysteric acid oleogel. Let's go back to, we're just looking at applications, hydroxysteric acid, and we did an in vitro test. Imagine if you have an in vitro test, you have some sort of emulsion with the hydroxysteric acid and the beta carotene in there, and we hit it with an enzyme, and the enzyme starts breaking down, and outside it's a surfactant, and the beta carotene goes from inside your emulsion to this micelle. This micelle, I forget what surfactant we use. But it's beta-carotene micellization, and it becomes redder and redder as things degrade it, as the enzyme degrades it, and it leaves your little emulsion. And so you can see how, in this case, which would be just the oil itself without the oleogelator, immediately after 30 minutes incubation time, you have just released as much as it's going to release. Now you put it in the oleogel, and in vitro at least, there's a controlled release. There's a slowing down of the release. The oleogel somehow is keeping that beta-carotene in there and preventing the enzyme after its degradation from releasing it. So the oleogelation has a role in slowing down that process. Then we went out and found a whole bunch of you out there and promised to give you like, I don't know, candy, and bled you. I call them feed and bleed experiments. So 25 people, you give them like a whole chunk of hydroxysteric acid oleogel. I don't know how I got that through the ethics committee, but I went through it. They let me do it, so I fed people a ton of hydroxysteric acid, about 50 grams per thing. And then we bleed you for 6 hours. Some people call it clinical trials. I like it feed and bleed grad students. And so what we do is we feed them butter, margarine, canola oil, or the organogel of the canola oil, and we didn't find anything. It wasn't doing it. The only thing it did is that it behaves like the oil. Look at those two squares. That's the oleogel and the canola oil versus the difference in triglycerides that you would get from butter or margarine. And the butter's the one that raises your triglycerides. That's a marker of your health. Maybe you go to the doctor, they make a blood test and say your triglycerides are 100 millimoles per deciliter. So this is what we're doing. It didn't change C-reactive protein. It didn't change HDL, LDL, all the lipoproteins, but it did change how much of the triglyceride was showing up in your blood. So it's gelled, but it behaves like oil. At least is one thing we saved the whole study. We were thinking like it was going to be a massive thing, but whatever. So that's just the same as I showed you before. The other thing you can do is, what about gelling and emulsion, and water and oil emulsion? And this has a dye. It doesn't see very well. So when it phase separates after 21 days, you can see here this is clear in the 80-20, but if you add the hydroxysteric acid, you don't have separation of the water phase from the oil phase. So it slows down the breakdown of emulsions. And if you look at this under polarized light, you see your very large droplets. This is emulsions made like this, right? Of water in the oleogel. And look at the birefringent things I showed you before. It just sets in there and stabilizes the emulsion. And Arenbot had the same idea, and he shows how his phytosterol safins, his self-assembled fibrils, are stabilizing the same thing. So very nice system in order to be able to prevent phase separation of things that would otherwise cream like crazy. And it seems to be stable for like 21 days at room temperature. Very quickly, okay, I have more examples, but I'm just going to do. These are very famous because they're widely available. They're byproduct of something like the winterization of sunflowers, and waxes are very effective at low concentrations, derived from natural plant sources, and commercially widely available. If you ever get the weird idea of working in these things, please do a chemical composition, because they're highly variable as they come. You can buy them commercially that they've been highly refined. Now, when I tell you the word wax, you think ester of long-chain fatty acid with long-chain alcohol. Maybe, but it also has free fatty alcohols, free fatty acids, resins, and all kinds of stuff that comes from the waxy cover of a seed. So there's a lot of crap in it. So make sure that you clean it, do something, or at least chemically determine, which is very difficult, by the way. I'd say clean it. or buy it clean, refined. Otherwise, you're going to get different results. And if you ever want to buy a batch of really bad gelling rice bran wax, I'll comply. I bought for the first time 25 pounds of the wax, and it's crap. It doesn't gel till 8%, and I have a cupboard full of that thing because it costs a lot of money. So beware, do not make the mistake. That variability is terrible. Rice bran wax has a nice name, right? Rice bran wax, sunflower wax, Candelia, Carnauba is for your car. So minimum gelling concentrations, look at that. You can go down to 1% for the different waxes, 2%. And this is what I was telling you about the composition. You can look at that. Don't forget, it has free fatty acids. Look at this guy, Candelia wax, 7 to 10% fatty acid. So you don't even know what you're structuring. And like fatty alcohols, another 10%. So, and that you think you have waxes, esters, but you don't. And as a matter of fact, this one is really interesting. Candelia is a cactus from the Mexican Altiplano. And they have a lot of hydrocarbons. Look at that. It's like mineral oil-like, if you hate plant systems. If you do X-ray diffraction of waxes, it's extremely boring and extremely beautiful. You actually see always a pattern that is corresponding. This has been indexed, so you know what plane it is, and it never changes. So forget about it. Don't do diffraction of wax. This is the most boring thing on earth. It always comes out like that. So you don't see, but you do see some action in the small angle region. You actually have lamellar organization of the waxes. Nobody talks about that. Lamellar organization, and some waxes are more highly ordered, and you see the 001, 002, 003, 004 reflections of that lamella. Notice here in the sunflower wax is not as drastic. They have different sizes, whatever they like doing. And when you go to Candelia wax, the peaks start getting wider, so the crystals are either smaller or highly disorganized. And in something like Carnauba wax, you don't even have a sax pattern. So there's something to say about the nanoscale organization of these waxes. The typical diagram that you would do, the melting point as a function of concentration. Both you can do some solubility analysis of this. But regardless of that, notice how you have to be really, really low before you start dropping that melting point, right? So this, you go like that, and if you're the boss in the company, you go, that thing is going to be a crappy fat. It's just not going to melt. I mean, 60 degrees Celsius, and you're like working already at 5, you have to go to like 1 or 2%, and you only get to 55. Problem with these oleogelators are their high melting points. Of course, this is the G prime behavior. They can have fairly, and at that time we were always plotting oscillatory stresses. We were not interested in the Laos region at this time. But you know, different waxes do different things, but if you need to know, they're between 1 times 10 to the 6 and 1 times 10 to the 5 pascals in terms of concentration, and they have different yielding behaviors that could be interesting now that we're more interested in Laos. That looks like a nice system to study, actually. And we are beginning to do that. We're actually using your nonlinear programs to study what happens when you crystallize waxes under laminar shield fields, like in a couette cell. And you can really induce plasticity by doing that, by crystallizing in a laminar shield field. The only problem is that they also get super weak. So I do not know what to do with it. Then we also study oil binding with a very advanced machine. This machine is ultimate. This is like proto-rheology. You put your thing in a thing with a filter paper, and you just look at how much it drips. But then you don't say that too loud, and then you fit it to models, and people think that you're like a genius or something. And then you have like double exponential increases, and you can characterize the way that it releases oil extremely well, and you can put rate constants to it, but whatever. I mean, maybe at the end of it, I would just like to know how much oil was released after like a day. But you can also do a graph like that if you want. Then we were analyzing what was the deal with that. And so we have rice bran wax, sunflower wax at their critical concentrations, even a little bit higher. This is the maximum leakage of oil. Notice how nicely Candelia wax caught the oil. Very interesting. Box counting fractal dimensions of the images of polarized light. This one has the highest one. So more homogeneous distribution of mass, more space filling if you interpret your box counting dimension by microscopy. I wouldn't trust this number too much because it was never made for waxes. And then if we do porosity as 1 minus the percent fill from your image analysis, you can see that your porosity is lower because it has a higher box counting fractal dimension. That's what the image is telling you. You would think that then the Candelilla wax makes things that are less porous. And also, it makes very small crystal lengths. So Candelilla is cool because it makes little crystals, and it's when you look at the photograph, there's a more homogeneous spatial distribution of mass, more space filling, homogeneously space filling, that we interpreted as lesser porosity. So Candelilla is doing something interesting. These things leak like crazy, by the way. And we do bright field microscopy, and you see some of these. Look at that spiders coming around, and some of them are less spidery, but definitely Candelilla wax. CLX, look at it, looks more coarse as opposed to these things that look more, this is thick, spherilytic, or some people call those needles, but that was a confusion, the needle thing, we think. I think I told you that crystal size can be affected by this thing. But then we said, why do we have needles? Like, needles what? Waxes, if you look at all the literature in waxes, they form platelets, right? So why don't we go to the SCM and do some like etching with an organic solvent called and let's see what we get. And we found that a whole bunch of these platelets were just sitting up like this. They weren't needles. They were like platelets standing on their side. And that was what's giving us some of the morphology that we associated. And we put out there that even though you think that you have needles, if you call these needles from a micrograph, in reality you just have, this is what we got from the SCM. We actually got platelets that were in there. But they were on their side, FYI. Yep, and I can finish with the ethyl cellulose. So I told you about two systems, interesting systems. People are still exploring how to control it, still uncontrolled. They're brittle. It's happening right now that people are trying to make these things work. Ethyl cellulose is really cool. You buy ethyl cellulose, you heat it up above its glass transition temperature, you cool it down, and you form this incredible gel, completely translucent. And everything you know about hydrogels applies to oleogels. Ethyl cellulose is just a cellulosic, it's a linear chain of glucoses with a beta-1,4 link, as we learned. The other thing, and you have the possibility of putting 3 substituents max in it. And most of the time, it's mostly filled. The degree of substitution is something like 2.4 to 2.5. So you have these ethoxy groups hanging out from the OH groups. And you get different solubilities depending on the degree of substitution. You can have a basic aqueous solution, water solution, or dissolve in polar and non-polar organic solvents. So you can do a lot by that degree of substitution. Now, Dow would not tell me what molecular weights these ethyl cellulose have, because they're like evil. And they sell it to you according to the viscosity of a 5% solution of ethyl cellulose in toluene ethanol. Because we all know that viscosity is related to molecular weight. But they don't promise you a molecular weight. Why? Why? Because they're evil. Because you can mix things and get to that viscosity, right? So they just sell it to you with a 4 centipoise. I love those units, better than angstroms, centipoises. And I'm going to start talking in ergs very soon. And we had to set up the HPLC with toluene. You know, nobody does this kind of crap anymore. And size exclusion chromatography. And there you go, for your benefit. They're between, you can buy things very, very, some polydispersity, but even commercially from 11 kilodaltons to 70 kilodaltons. It's a good range. So you can mess around with molecular weight. And here is the glass transition temperature that we can detect around 120 degrees. And this, Dow calls that decomposition, but I think that that's the melting of the still crystalline regions that are in this amorphous cellulose. You still have that stuff. And so if you're lucky, you can unravel this before you burn it, because that's what happens. So you heat it in the oil and you get the ethyl cellulose oleogel. So that's the glass transition temperature you have to go above. You better do it under nitrogen if you want to eat this afterwards. And then you cool it down and you form this thing. You can make this gigantic piece of gel. If you do a mechanical test according to the texture profile analysis, 50% compression, parallel plates, you can see how, look at that, you can make it with different oils, flaxseed oil, soybean oil, canola oil, and you can get different hardnesses from the oil you choose. Woo, it's a mystery, right? And we have a bit of an explanation for that. And this is also, the effect of molecular weight. So you can go from low to high, and it makes sense, right? Higher molecular weight, stronger gel. You can adjust the composition in terms of a ethyl cellulose concentration, a co-surfactant or plasticizer, which could be another food-grade surfactant, and here is some sort of a gel strength in terms of the mechanical hardness. So you can play with all of that, and you can actually get a plane, and you can substitute one composition with the other composition for this particular 20 centipoise molecular weight with sodium monosterate, and you can predict a little bit what of the hardness you can get. So very flexible in creating different mechanical properties of the material. You have to be really careful because these materials are sensitive to the type of oil you use. Castor oil is a very polar oil. Mineral oil is mineral oil. And also the small molecules that would potentially act as a plasticizer or structure enhancer. So you can invent some combination that has some magic property. So if you notice here, as you, this is just concentration, this is the mineral oil, the polarity goes down as you put mineral oil because it's less polar, right? And the more castor oil you put, the polarity goes up. And look at the relative force. The relative force goes up the more castor oil you have, and it goes down with the greater mineral oil content. So if you manage to unravel making a good solvent, right? You make a good solvent by mixing canola oil and castor oil, maybe a theta solvent. Nobody has talked about that yet for organogels, for the oleogels. You make a stronger gel, which is related to the polarity. Very interesting behavior that hasn't really been waiting for one of you to do it. So solvent polarity lives. I'm not gonna really cover this, but you can explain it using Hansen solubility parameters. So you have the polar, the hydrophobic, and the dispersion forces, and you have this cohesive energy densities, right, that are tabulated for the different polymers and solvents. And the closer you are in terms of these terms to the solvent to the polymer, the more it will dissolve into each other. And you can calculate a distance between your polymer and your solvent by Hansen's formula, which is a little bit empirical. And so if this radius, this distance between your polymer and your solvent is like yay, and you also need another parameter, which is the radius of influence of your polymer. If that is smaller than the radius of influence, they're within each other, within a certain range, they're soluble in each other. And that's how they judge. That's how Hansen judges. Does it work? It doesn't work too bad. And you can get tabulated values for the Hansen parameter. And if you have a combination of two, don't be brave, don't put three, of two different solvents, the effective in the cohesive energy densities are just the linear, the volume fraction weighted mixture of the two. And that's where things start breaking down anyways. We found that the better predictor of viscosity was the difference in the hydrogen bonding component in an oil between the polymer and the oil. And you can see very clearly that you have a minimum difference between your polymer and your oil at around 80% castor oil. And 85% castor oil has the highest viscosity. So you get that sucker in solution by adjusting the polarity or the Hansen solubility parameters. It unfolds to the point where you make more viscous, it's more unfolded, it's a lot more functional. You can bind small molecules and enhance the strength and then decrease the strength. You can go this on your own. I'm not going to talk about T2 relaxation, but I did want to make a last showing you the atomic force micrograph of these things. We may spend a lot of time characterizing how these look. That egg carton model, these things are crazy. They form this crap, the ethyl cellulose. And be careful sometimes when you do this study. So first compression hardness, we said that there's 3 different oils with 3 different hardnesses. So what about the pore size of that egg carton? That goes up and the pore size goes down. So small pore size, harder gel, right? Right. So molecular weight, as you increase the concentration, you increase the gel strength. When you look at the pore sizes, you increase the gel strength, but you decrease the pore size. Amazing. Twice it worked. By the lottery. And then what about this? Of course, it works anytime. You increase the gel strength, the hardness, by going to a higher molecular weight, 45 to 100, 45 to 100 with soybean or canola oil. So we're expecting the pore sizes to become smaller, but they remain the same with molecular weight. So the conclusion was that in this particular study, we have it's the wall strength. So you need to go back to like the Ashby models and look at the of the hardness of the walls, and the molecular weight affects the hardness of those walls, which affects the mechanical strength of the material. But there's a huge element of both the size of the pore and the strength of the walls that make up that egg box. Maybe it's not that surprising, but it was a molecular weight related effect. So you can change one independent of the other one, which is not a bad thing to study. Now, I left you in the study there other examples. I'm encapsulating beta-carotene, releasing it. We fed this to another bunch of unaware graduate students, but in Singapore. So I'm just going to show you that one graph here. And it's really interesting. Rice pudding. So the breakfast tomorrow is rice pudding, and it may feel a little fatty. And if you feel a pinch, disregard it. It's just me going around pinching your thumb. They do it with thumbs now. They don't like. And if you eat, look at this. It's so cool. If I give you 50 grams of coconut oleogel, 50 grams, in your rice pudding. And this was done, unfortunately, sorry ladies, 20 healthy Chinese men. Because I don't know why in Singapore they just bled. Maybe the women were too intelligent. Like, you're not bleeding me, and I'm not eating 50 grams of like coconut oil pudding. But that's in this study. So, and then we bleed you for this long, 6 hours. If you actually just have all the coconut oil, same amount of fat. This is the coconut oil. Look at you more or less get this when you eat a fatty meal, like a Big Mac and fries. After more or less, divide that 4 or 5 hours, the fat is hitting your blood. That long it takes. But if you use the same amount of fat, either coconut oleogel and the control with no fat, look at that. We absolutely lowered that triglyceride loading in your blood. So you can really control. Remember how the triglycerides were important in the other oleogel as well? So by gelling the oil, you're slowing down, makes sense, right? The release of fat that eventually gets absorbed into your system. So really cool thing affecting biological, and these are humans, not rats or anything like that. It's easier to do it on humans. So anyways, the potential's there. A lot needs to be known. Thank you for your attention.